this video lecture, we will look into how to compute the derivative of unit vectors of the Cartesian and the polar coordinate systems with time. So consider a vector denoted by RT at time t. To simplify notation, we may drop the time index and just write vector r. The derivative of r with respect to time is denoted by the equation you see here in this red box. Derivative of a vector with respect to time shows how a vector changes with time. Every vector r embodies two pieces of information, magnitude and direction. So the changes in a vector with respect to time can be only in magnitude, only in direction, or both in magnitude and direction. So when we want to compute the derivative of a vector with respect to time, we should ask what changes the vector has gone through. Has its magnitude changed? Has its direction changed? Now let's represent our vector in a coordinate system. The two main coordinate systems we use in this course are Cartesian coordinate system and polar coordinate system. Let us assume that our vector is the position vector of a moving particle. In Cartesian coordinate system, the position vector of an object at time t is expressed as its x-coordinate at time t in I direction plus its y-coordinate at time t in j direction. In polar coordinate system, the position vector of an object at time t is expressed as its radial distance r from the origin at time t in er direction. Now to compute the velocity of the object in Cartesian coordinate system, we take the derivative of the position vector with respect to time. Using the chain rule, we arrive at this equation. Now you can see that the derivatives of unit vectors show up in our equations. Now the question is, what are the derivatives of these unit vectors? The magnitude of any unit vector is always 1, so the magnitude is not changing with time. The direction of unit vectors of the Cartesian system is also fixed and does not change with time. So no matter where the particle is, the direction of I and j unit vectors are all fixed in time. I is always in x-axis direction pointing to the positive sense of this coordinate, and j is always in y direction pointing to the positive sense of y coordinate. Therefore, we can conclude that the derivative of these unit vectors are 0 because these two vectors do not change with time. Now we may ask, is the derivative of any unit vector of a coordinate system 0? The answer, as we will see next, is not necessarily. Let's consider the polar coordinate system. To compute the velocity of the object in this coordinate system, we take the derivative of the position vector with respect to time, just like what we did in the Cartesian coordinate system. Using the chain rule, we arrive at the equation that you see here. Now you can see that the derivative of unit vector ER shows up in our equation. The derivative of unit vector E theta shows up in the acceleration equation. So I'm going to skip those details. Now the question is, what are the derivatives of these unit vectors of the polar coordinate system, ER and E theta, with respect to time? The magnitude of any unit vector is always 1. So we know that their magnitude is not changing with time. But as we can see in this demonstration, the direction or orientation of the polar unit vectors may change with time unless the object moves on a straight line. Therefore, the conclusion is that the derivative of the unit vectors ER and E theta, they are not necessarily equal to 0. But what are these derivatives? For a unit vector, therefore, the change with time is due to the change in its orientation, which is due to the rotation of the unit vector. Therefore, we can expect that the rate of change of a unit vector with respect to time is a function of its angular velocity. Indeed, it has been shown that the rate of change of a unit vector with time is equal to its angular velocity cross product with the vector itself. In a two-dimensional space, the angular velocity vector is always in the direction that is perpendicular to the two-dimensional plane. Let us denote the unit vector in the perpendicular direction with k hat. Then the angular velocity in the two-dimensional space is omega, which represents the magnitude and the sign in the k direction. We will always assume that the positive direction for k is pointing out the plane and the positive sense of rotation is counterclockwise. Now with these informations at hand, we can compute the derivatives of the unit vectors of the polar coordinate system with respect to time. The derivatives will be the angular velocity of the vectors cross product by the vectors themselves. The angular velocity in polar coordinate system is going to be theta dot in the k direction. Therefore, when we substitute in the formula, we can arrive at the equations that you see in the black box for the derivative of the unit vectors. Theta dot in k direction representing the angular velocity cross product with the vectors themselves. Now, if we carry out the cross products, the final equation for the derivatives will be as shown in this green box. So in summary, the derivative of unit vectors of the Cartesian coordinate system with respect to time are 0 because these vectors do not change with time. Both their magnitude and directions are fixed at every time t. However, in the polar coordinate system, the derivative of unit vectors with respect to time are not necessarily 0 because the orientation of the vectors are changing if the object rotates with an angular velocity of theta dot. The derivative of ER with respect to time is theta dot in the E theta direction, and the derivative of E theta is minus theta dot in the ER direction.